Hello everyone, this is part one of what I'm hoping to only be a two-part video. So we're just going to get started. And this is section 2.2, graphs of polynomial functions. And let me say this, I know we're doing this new format and you all may or may not like it, but it's really more so to make sure you retain information better, which means it's going to be more responsibility on you all to read ahead. Well, not read ahead, but you can. But to make sure you watch these videos before class, take notes on anything because although you'll be working in groups, I still will be answering questions throughout your groups. Or if there's a general question that everyone is struggling on, I can do a mini lesson for you all. But my goal is to have you practice these problems. That's how you're going to become proficient in this class, and not just become proficient to pass this class, but to be able to go on to the next sequence and do well as also, or the next course, math course you have to take. Okay, so let's get started. So this is polynomial functions, which this whole chapter is about polynomial functions, and 2.1 we looked at quadratic functions. But now these are polynomial functions. The nice thing about polynomial functions is that they're continuous. Okay, and so they're continuous. And so if we have, so for instance, continuous means it's smooth. For those that remember continuous, another way to tell if a function is continuous, if you can start from one end of your graph or your picture, your function, and trace the function without having to pick up your pen because there's no gaps or jumps, then that's also continuous. So this is an example of a continuous polynomial. So this is continuous, and I'm going to use CONT for short, and polynomial, POLY for short, and FXN short for function. So this is an example of a continuous polynomial function. So something like this would not be continuous. So it's not continuous. And since it's not continuous, that means it's not a polynomial function, right? This is actually a piecewise. This will be a piecewise function. And it's not a polynomial function because polynomial functions are continuous, okay? Also, a polynomial function has only smooth, rounded curves. Oh, that's right, and it's not bad. Okay, let's erase that and rewrite. Rounded curves. Okay, and so again, so in this first picture here, so in A, notice that this curves were rounded smoother. Here wasn't continuous because there was that jump there. But so another example, we can have something like this. This is a smooth, rounded curves. So if you had something like this, which you all know as this is f of x equals absolute value, right? Function. There is a sharp point at the origin. Okay, and that's why when you guys were sketching in the earlier chapters, I wanted you to be careful because it has to be round and smooth, your curves. If you have any sharp points, and when you move on to apply calc, you'll learn that means something dealing with derivatives and differentiable and things of that nature. So just keep in mind that your polynomial functions have smooth, rounded curves, and so that's very important. Also, the simplest of polynomial functions to draw are monomials. All right, mono, not the disease, means one, right? So it's one term. So in general, f of x equals x to the n. That's what we call a monomial, where n is greater than 0. Okay, so that's a monomial. Oh, and n is an integer. So n, I'm sorry, I hope you can see how I scrolls that in. N is greater than 0 and n is an integer, okay? You may recall if there are two terms, these are all types of polynomials. So we call that a binomial, right? And so, for example, we could have f of x equals negative x plus 2. That would be an example of a binomial. And then many terms are poly. All right, poly, the root word poly means many, so many terms. So monomial means one term, binomial means two terms, polynomials mean many terms, which is from the root if you know about polygamy. I don't know why I'm bringing that up, but many wives is polygamy. So poly means many. I just want you to know the root words and what they mean. Bi means two, and the mono means one. Okay. All right. So now, and you'll see that I can't continue on one page for some of your notes that are on one page, so you should be on the same page. So when n is even, the graph is actually similar. So for any even functions, the graph is similar to x squared. When we're talking about monomials, in general, it sort of takes on similarities, but we'll talk about that later. But we're focusing on monomials. So for instance, if you had g of x, we're going to actually plot x to the fourth, x to the sixth, etc. They all take on the same shape, which is the parabola. And if n is odd in our terms of our monomials, they look like x cubed. So that would be, let's call it h of x would be, let's say x to the third, x to the fifth, x to the seventh, etc. They would all look similar, okay? The thing you need to keep in mind, and if you think about it, the larger the value of n, the flatter the graph is near the origin. And the reason for that is just think about near the origin, the values are fractions, right? So between 0, 1 or 0, negative 1 and 0, you have, take for instance, 1/2. If you plotted 1/2 into this f function here, if you plotted 1/2 into our f function, then, so if we plot into the f function here, 1/2 squared is 1/4, right? But just imagine if you plot 1/2 into x to the fourth. Well, that's 1/2 to the fourth, which is going to be very, very small. So that's why it's very small near the origin. So graphically, let's see. Okay, so I'm not going to spend too much time on showing you in terms of sketching of these higher level graphs, because we're going to learn other techniques. But I just want to sort of emphasize a little bit what I mean by the larger the value of n. The larger the value of n, the flatter the graph is near the origin. So if we take a look at x squared, this is just our parent graph. X to the fourth is going to take on a similar shape, except, actually let me use a different color. It's going to be, its values around the origin is going to be more so towards the origin. So you see how that's a little flatter, and then it'll come up. Okay, so that's what it means by the flatter near the origin. It's a little more flatter. And if you were to look on a calculator or to plot points, you would see why it's flatter, because the numbers, if it's x to the fourth, the numbers around the origin are going to be really, really small. Okay. And then similarly here with our, it's going to be a little more flatter around there. So that's all I mean when I say, so this could be a possible graph for h of x equals x to the fifth, and this could be, let's say, v of x equals x to the fourth. Okay, so it takes on the same shape. These are just monomials. When we get into more graphing other polynomial functions, you'll see in a minute. Okay, all right, so let's move on. Just wanted to sort of talk about that. On page 2, this might be 3 videos. I'm really trying to keep it under 2 videos, but we'll see how we go. Okay, so the leading coefficient test. Now, a lot is going on here, but it's really pretty simple in understanding this, so don't let all this throw you off. It's really simple. The leading coefficient test, the purpose of the leading coefficient test is to let you know the long-term behavior of your function as x goes to positive infinity to the right and negative infinity to the left. So we say that that's as x moves without bounds to the left or the right. That just means as x goes to positive and negative infinity, the graph of a polynomial function will eventually rise or fall. And it depends on a couple things. So when you have your polynomial function, it really just depends on looking at the largest degree. So look at the degree, because it might not be in descending order. And so you look at this value here, and if n is odd, so you look to see if it's even or odd. And then you look at your coefficient in front of your leading term to see if it's positive or negative. Okay. And I'll tell you a couple things. So here's the different combinations. And you have it on one page, but I had to break it up into 2 pages. So if n is odd and a sub n, that leading coefficient, is positive, then that means as x goes to positive infinity, as x goes to the right, the function will go up eventually. And as x goes to the left, the function will go down eventually. So that's if n is odd and a sub n is positive. If n is odd and a sub n is negative, then it flips. So now as x goes to positive infinity, the function goes down. And if x goes to negative infinity, the function goes up. Now remind me in class on Friday to show you sort of a trick in understanding this better, and sort of if it helps you, you can use it. If not, just you need to remember these combinations. So this is when n is odd. Now when n is even and a sub n is positive, then they both go up. As x goes to positive infinity, f of x goes to positive infinity, and as x goes to negative infinity, f of x goes to positive infinity. And if n is even and the leading coefficient is negative, then they both go down, okay, to the left and right. All right, so that's the gist of this. Now let's look at example 1, our first example. Describe the left and right hand behavior of the graph of each function. So again, we're looking in this example 1. What's our n? Our n is 3, so it's odd. And our a sub n, okay, is -1, so it's negative. So looking back on that sheet, we have odd and negative. So we have this situation here, right? So that means as x goes to positive infinity, our function goes down, and as x goes to negative infinity, our function goes up. And so that's the answer. You would say as x goes to infinity or plus infinity, you would say f of x rises, or I'm sorry, it falls. It's the other way around. Falls. And as x goes to negative infinity, f of x rises. And I don't know if I've used this notation before, but this is saying x goes to. So we abbreviate a lot in mathematics. So this is saying as x goes to negative infinity. Okay. So hopefully that makes sense. Again, remind me on Friday and I'll show you another way you can look at this if that's not making sense, and hopefully that'll help you. All right. And then for number 2, n, so see if you can do this on your own before we go, but n equals 4, a sub n equals 1. So we have an even positive, so that's greater than 0. So it's even and positive, so they both go up. So we would say as x goes to positive infinity, f of f, or f of f rises, and as x goes to negative infinity, f of x falls. Okay. Or you could have said as x goes to plus or minus infinity, our function rises. Oh, rises. What am I doing? Sorry, you all. All right. And if anything isn't clear in these videos, just let me know. So I'm going to finish this page and then I'll stop the video. So for a polynomial function f of degree n, the following statements are true. The function f has at most n real zeros. The graph of f has at most n minus 1 turning points. And turning points are called relative maximum or minimum. And there are points at which the graph changes from increasing to decreasing or vice versa. Okay, for sake of time, I filled in this last section here. So the following facts are equivalent. Now we're going to go over this in the next video, so don't worry. So let f be a polynomial function and r be a real number. The following are equivalent. And what equivalent means is that if you know one fact on this list, then you know the other 3 and vice versa. They're interchangeable. So if r is a real number, x equals r is a 0 of the function f.